good morning and good afternoon, wherever you are. And this is Hong Hai from Vicksburg. And today I'm going to present another topic. And it's multiple size sediment transport. In the first I will present some background information, some theories, and then I go to SMS, use a case we did before, which is Fort Pierce, Florida, and you can see the picture on the right hand here, and but the model not well calibrated. So just for the demonstration of this feature in CMS. And the most material I present here is in these two publications. One is Coastal Modeling System, Mathematical Formula and Numerical Method. That's a published early tech report. And the other one is a Coastal Modeling System User Manual. And this one is an unpublished version. And we are going to update this manual and get published in next fiscal year. And so there's a link for both publications here. And so if you have interest after the webinar, maybe you can download those reports if you haven't done so. And also there's a lot of general paper, many general paper published related to this topic. And yeah, that's the publication. For the presentation, my outline is sediment transport in CMS. First, I have some theoretical equation or explanation. And then I come to multiple size sediment transport calculation. And there are some concepts related to multiple grain size sediment transport calculation. So I will go over that through some concept, like transport grain size. What's transport grain size? How do we specify that in the multiple grain size transport? And also bed layering, and how do you discretize a vertical bed layer? And also bed composition. And after that is introduce other parameter. Other parameter is not only for multiple grain size, also for single grain size sediment transport. And then when we set up CMS and set up the modeling simulation, we export the CMS file and then make the model ready for real simulation. And this is a test case I mentioned for multiple grain size sediment transport. And on the left-hand side, there's a data tree. And different from a single grain size transport. For single grain size transport, for bed composition, you only need to specify D50. And but for multiple grain size, you can see here we have a different option to specify bed composition. And here is one option. We need to specify D60, D50, D84. And I will introduce some other specification for bed composition later. In more detail. And also for multiple grain size simulation, you need to specify the bed layer thickness. Because you have a number of vertical layers you need to specify. For each layer, you need to specify the thickness. And you can see there's a extra data set here, thickness layer 1 and thickness layer 2. The way to generate those data set is the same as Mitch introduced, like last 2 days. And you go to data set calculator and then generate those data set. And also, at the beginning, you can assign an initial value for that. And then when you generate those files, and then you can do 2D variable and bed thickness or bed composition, change those and finalize it. And here is a non-equilibrium total load sediment transport equation used in the CMS. And first, I have a definition of those terms. And you can see CTK is the depth average sediment concentration. And K is the sediment size class. So that's one sediment class for transport. You pick transport class, right? So K is one of the sediment size class. And CTK star is the depth average total load concentration at equilibrium state. And beta TK is a correction factor. This is a ratio of depth average sediment and flow velocity. So it's a lag between flow and sediment. And this parameter was calculated in the model. But later on, when I go to interface, you will see for some transport formula, you need to specify vertical profile. So that's the purpose for calculate this parameter, the correction factor. And UC is a resultant velocity of current. And epsilon S is sediment diffusion coefficient. So RSK is a ratio of suspended load to total load. So as we know, this is a total load equation. So the ratio of suspended load will give a portion of the total load for suspended load transport. And 1 minus RSK apparently is a bad load. So that's bad load. So bad load plus suspended load is total load. So that in that equation, and RSK is needed too. Alpha T is a total load adaptation coefficient, and adaptation and also sediment omega S is sediment fall velocity, and LT. This is the equation equal to UCD over alpha T omega S. So you see here, total load adaptation coefficient is related to this LT, which is the total load adaptation length. So from the very right-hand side is UCT sub T. So the length and time both related to alpha T here. So from definition of alpha T, total load adaptation coefficient, we define LT is the total load adaptation length. And the TT is the total load adaptation time. So what this parameter do is like adaptation total length is the distance it take for the sediment from non-equilibrium to equilibrium. Yeah, I will describe this later in more detail. And after defining those terms, so we can check the equation. So apparently, first term is a time derivative of sediment concentration. And the next two term is advection term. And then on the right-hand side, and then first two term is a diffusion term of concentration. And it's related to epsilon s and depth. And also RSK, we know is a suspended load, portion of a suspended load. So this is a suspended load transport. And then the last term is a source and sink term. It's basically is a erosion and deposition term. And you can see here, and so it's controlled by the CTK star. So CTK star is a equilibrium concentration. So it's a sediment capacity. And so the right-hand side, of course, is like a forcing term. So we call this sediment transport model, and in CMS. So the low right corner, you can see in the CMS SMA interface, we have a different option for the sediment transport model. And as you understand, we present this merged code. In merged code, we have two solver, one explicit solver, one implicit solver. So we are introduced mostly concentrate on implicit solver. Currently, for implicit solver, so we have only one option. It's a non-equilibrium total load sediment transport, which is this solve this equation. And for the explicit solver, maybe some people still use explicit solver, and you have other option. So both are equilibrium total load, and also equilibrium bed load plus non-equilibrium suspended load. So in implicit solver, we have a default, so non-equilibrium sediment transport. And when we're talking about sediment transport model, you remember we often mention sediment transport formula. So don't confuse about these two concepts. And sediment transport formula, the purpose we use is for calculate CTK star. And here, we used to calculate CTK star and sediment capacity in the model. And so next, we will introduce sediment transport formula to calculate this sediment concentration and concentration capacity. And the option in the CMS, we have currently in the interface you see 4 options. So which is Longserp, Fanrai, and Sotheby Fanrai, and also Watanabe. And lately we are adding another model we call C-Shore or C2-Shore model, developed here by Brad Johnson. And we are doing some testing. And this model addressing the surf zone process and near-shore, cross-shore transport. And so later on, after we finalize this testing or merging with incorporated with the CMS, so we will put that in the interface 2 for another option for transport formula. And those transport formula are very important parameter. Selection for the during model simulation. And when you set up a model simulation, it's a very important step to check different formula for getting your model simulation result. And right now, the default formula is a Longserp. And sometimes we check Fanrai and Sotheby Fanrai and to compare result and select a proper one for project. So after the sediment transport model and sediment transport formula, so the next one is a bed change. This is the equation for bed change due to K class of sediment. And PM prime is a porosity of bed material, and ds is coefficient for bed slope effect. And QTWX and QTWY is the sediment transport rate due to wave asymmetry and undertow in X and Y directions, respectively. And so you can see the bed change on the left-hand side, partial ZB, partial T, is related to the controlled by the right-hand side terms. And the first term is erosion and deposition term. And this is same term appear in the sediment transport model. And second and third term is a bed load transport part. So you see here why I say it's a bed load, because you see the portion of the sediment is not total load, it's 1 minus RSK. And also there's a coefficient for bed slope effect here, ds, also contained in these two terms. ds is also a very important term for model calibration. And it's mostly, as you can see in the equation, is a control the bed load transport. And currently, I think the default value is 1 bed load. Sometimes when we do model calibration, we adjust this parameter from 1.1 to 1, maybe 2, 3. And there's a range, and I think from 0 to 5. So I will mention that when we specify the setup for the real case. Single grain size sediment transport, that's the one we use before most of the time. And as you probably know, sediment transport is a hard topic for model simulation compared to hydrodynamic and wave simulation. And so at the beginning, most of our model just handling single grain size. So it's not a real situation in reality, right? So, and later on, multiple grain size, cohesive, non-cohesive transport will develop. And we talk about multiple grain size. How do we judge a system? Which scenario we use? We use single grain size transport or you multiple grain size transport. So here is a slide show, and when we determine which case we use multiple grain size sediment transport, we base geometric standard deviation. And the equation given here, so sigma g equal to exponential square root sigma pt log dk minus log dg, and with k exponential. And pk is a fraction of k grain size. And dk is the size class diameter. And dg is the geometric mean. So geometric mean is given by this formula here. And here is a right hand is a table. And based on the geometric standard deviation, so we get some number here, right? The number is small number is well sorted, and big number is poorly sorted. And based on our experience, if geometric standard deviation greater than 1.4, around 1.4, 1.5, and we should use multiple grain size simulation and take this option. So next, I talk about transport grain size. Transport grain size. And on the right-hand side, you see this figure, right? So the bottom is a bed composition. And the particle in the air is, no, in the water column, I should say. The particle in the water column is a transport grain size. And of course, for single grain size, we only specify one grain size to do simulation and solve that equation. But for multiple grain size, we pick more than one. We pick more than one grain size. And the lower figure show there's a 6 grain size we pick for the Fort Pierce case. And it's through 0.1, from 0.1 through 6 millimeter. For each sediment size class, and we have those property here. So the first one is a characteristic diameter, right? And C on the right-hand side is 0.1, 0.21, 0.5. And then we have fall velocity. We have a shape factor. So shape factor affect the fall velocity, of course. And also for different grain size, we need to define that it has different critical shear stress. And next, I will show, so describe a little bit about how do we determine those property in CMS. Of course, most of them are calculated by some formula we pick. It's a default in CMS. And, but there's some difference here. So the first one we see is a characteristic diameter. And the diameter, you can see that once you pick a cat side, dk, so equal to square root, there's a range. There's a range. And so we use those formulas to determine the range of dk and pick a dk. And the reason behind that to pick dk is to cover the range of the sediment size in your study area. Like you can see in this example, we pick the size based on the data. Of course, we have some data show the sediment gradation core analysis. And then based on the data, we saw, in this area, sediment size is range from like 0.1 maybe to 5, 6, 7. And then when we pick transport sediment size, we try to pick the size from small to the big to cover the interested area. And in the SERP website, the wiki side, and we have put a MATLAB program. So if you go there, go to utility, you will find this program, and then use the program, and you can find sediment range based on D50, and you can get to the range of the sediment. And based on that, you can determine, you can pick transport classes in your model simulation. For velocity, and currently we have a different option. And we have a SOSP, Wu and Wang, and user specify. And right now, the current velocity, fall velocity is based on SOSP. It's a default. So basically, if you have data, you can specify your fall velocity. Fall velocity is of course, it depends on gravity, right? It's not a calibration parameter, and you either use existing formula, or you can do based on the data in your study area, like a user specified. That's user specified. And the shape factor, and shape factor only used in Wu and Wang fall velocity, because shape factor, so the shape of the grain size, so it affects the fall velocity, right? But in some other Sotheby formula, we don't need the specified shape factor. But only when you pick a Wu and Wang fall velocity formula, you need that factor. And so that's why it's basically, if we pick a Sotheby as default, and we don't need to specify this factor. And the critical shear stress also is a Sotheby, Wu and Wang user specify. And so it's also default is Sotheby in CMS. Most of the time, if we don't have data, we just use Sotheby formula to calculate and those parameters. And you can see the right-hand side. This is a different transport size class, and so you see the fall velocity method is a Sotheby, right? So fall velocity everything is default. It's a gray color for Sotheby, and the other like a factor is also gray, and but I didn't show you here. But later on, when we go to SMS, you will see and the entire picture. So after sediment transport model, transport formula, and transport grain size, and then next one is for multiple grain size sediment transport, we need to do bed discretization. And for single grain size, we don't need specify this. We only have one layer, right? But for multiple grain size, we need to do that. And the layer can be like a 5. You can specify 5 to 10. Yeah. But of course, if you have more layer, it will resolve the bed composition better. I don't know if we increase computation time. And for the case I use here, I specify five vertical layer. And the top layer we call mixed layer. So the left-hand side is for mixed layer. So that's the layer exchange sediment with water column. And this layer, some people also call active layer. So that's the layer, so have a communication with the water. So with sediment transport in the water column. So deposition, erosion, everything through that layer. And that layer, layer thickness has a typical range. You see here from 0.001 to 0.2 meter. And the default value is 0.05. So this is the initial layer. This is the initial layer. And in my case, I present here, I use 0.05. I use the default for mixed layer. And another way to do it, to calculate layer thickness. So which depends on median grain size, also bed form size. And the lower equation shows the way the model calculate mixed layer thickness. Yeah. So delta 1 is the thickness of a first layer, mixed layer. And HR is the ripple height. So you see this equation picks the max value of minimum layer thickness you specify, and 2 times D50 and half of ripple height. And the minimum between this one and the maximum thickness of the mixed layer. And this is how, if you use automatically method, and you will so calculate the layer like this. And the lower panel show the interface, how the interface looks like. And you see for the mixed layer, we have specified maximum bed layer is 5. It's 5 layer. And bed layer thickness, we need to specify minimum layer thickness is 0.05. Maximum bed layer thickness is 0.5. These two, minimum bed layer thickness and maximum bed layer thickness, is not only for mixed layer. It's all for all bed layer, for the layer below as well. And next one, we see mixed layer thickness. We can pick a constant. So constant, so that's what I described, is 0.05. You can do that. And also, when you click this tab, you will see there's a selection automatic. So for automatic, the model will calculate the layer thickness during simulation. And in this case, I specify constant. So I need to specify mixed layer thickness 0.05. So here. Yeah. And the layer communication is only when the mixed layer has an exchange with the water column. So as the figure show here, the right-hand side, so this is how layer change during a simulation. And when the first layer has an erosion case, and then the second layer will be split. And so there's in terms of layer-to-layer communication, it's only first layer and second layer has a sediment exchange. And the rest of layer has no communication, so has no change during simulation. So if there's a extra layer generated, if you have an erosion case, right? So you need to get material. If the layer becomes too thin, you need to get material from second layer and split layer. And if you go continue through a time step, on the right-hand side of this figure, you see accretion at the top. So if you have a accretion, and the mixed layer will have more material come in. And then if exceed the maximum layer thickness you specify, so the layer will be split into 2 layers, right? So you get an extra layer. So this extra layer will merge with the bottom layer, not in the middle. So you see the bottom layer in red color, right? It's in accretion case, it's become thicker. Right? And when you specify layer thickness, you can specify each layer thickness. But you can also specify a few layers you picked. And if you specify layer 1 and 2, in our case, you see that in the interface window here below. So we have thickness layer 1 and thickness layer 2. So we specify layer thickness in these two data set. So layer 3 and 4, 5, we didn't specify. But the model will copy from a layer, the thickness will copy from layer above. Layer 3, 4, 5 will copy from layer 2. And if you specify layer 1, 2, 3, so 4, 5 will copy from 3. Yeah, that's how we specify layer thickness. But you can specify all layer thickness in the model simulation. So after layer thickness, we talk about the bed composition. As I mentioned earlier, in all cases, all bed composition, we specify D16, D50, D84 data set. And there's a few options for user to specify a data set for bed composition for multiple grain size. For single grain size, you only need to specify D50. But for multiple grain size, you have a first option, and also you have option to specify D35, D50, D90 data set. And also, if you have data, you can so specify a different grain size. And like shown in right-hand side the interface, you can see you have a D5, D10, D16, all the way through D95. So this is based on the data. If you have data in your study area, you have those information, you can specify data set in your model preparation. And so in the interface, you can see, and you can link your existing data set here. Like this, I have D16, D50, D84, right? So you see here D16 for layer 1 and layer 2, I link to the same data set, has the same bed composition, and D50 and D84 here. And that's the way how you specify and link in the interface. Another way is to specify bed composition is to use the D50 data set. And just use D50 data set, but use the constant geometric standard deviation, as we mentioned earlier. So this way, model will automatically generate a bed composition. But right now, this is not in the interface. It can be done through advanced card. Like yesterday, Mitch showed you how to set up an advanced card, right? Advanced card dot sim card, and you can do this in that file. And I believe later on we can edit this to the SMS CMS interface. And also, there's another way to specify bed composition through size class fraction. So size class, each size class, what's the percentage it is occupied in the bed. And size class fraction is all the size classes should be added up to equal to 1. Yeah, there's another way to do it. So most popular way is the first two, and also if you have data, you can pick the third one. The fourth one is a D50 with a geometric mean. Standard deviation is very simple. You don't require to do much work, but right now it's in advanced card. Those are the multiple grain size specification and some introduction, some concept. And follow that is I call other parameter. This is a parameter not only for multiple grain size, it's also applied to single grain size. It's the same. So this is the right hand is how the interface looks like. And the first one, so you go to the sediment transport page, you check the calculated sediment transport, so you trigger sediment transport model. And the time step, and right now default is the same. It's same as a hydro time step. So you specify 600 seconds. So here is the same, and also for morphological time step is same time step. And the next one, you pick a sediment transport model. Yeah, as I mentioned, so sediment transport model for implicit solver is default is non-equilibrium total load sediment transport. So that's simple. But for explicit, so if you click this tab, you will see some other option for explicit. And the follow that is a sediment transport formula and concentration profile. So sediment transport formula is long SERP, Fan Rai, Salisbury Fan Rai, and Watanabe, and later on Seashore. And so here we show is a long SERP, which is the default transport formula. Concentration profile is Fan Rai. So concentration profile, as I mentioned earlier, is using for doing this correction factor beta TK, right? And after that is sediment density and porosity, and those two parameter is basically a constant. So it's constant. We barely change that one during simulation. And then after that is transport scaling factor and a morphological acceleration factor. And transport scaling factor is a calibration parameter. So we use very often during simulation. And default value is 1. You see the scaling factor, bed load scaling factor, and the suspended load scaling factor here. So in this simulation, we use a 0.2. We reduce to 0.2. We think after simulation and based on some observation data, we think 1 generates too much transport. So we reduce to 0.2. And morphological acceleration factor, default is 1. And we also use 1 here. And this is a factor lately we use for long-term simulation, like 100-year, 200-year simulation. We use, but it's a very dangerous factor when you use it to be cautious. And we find basically less than around 510 is a good selection. So any value like 20, bigger than 20 is generate unrealistic sediment transport and a morphology change. Bed slope coefficient, that's a parameter I mentioned early on in the bed load term of the bed change equation, right? And here we use 0.1, and sometimes we use 1 and change, and to compare with data, and pick a right one for that part. And hiding and exposure coefficient, and the default value also equal to 1. And hiding exposure coefficient, which if not only used for multiple grain size, it's also used for single grain size. Because in single grain size case, your bed composition is D50, right? But your transport grain size may not be D50, may not be small or big. And the interaction between the transport grain size and your bed composition can generate, can affect by hiding exposure effect. Yeah. And for multiple grain size, of course, you have different grain size, and the big grain size particle might hiding small grain size. Effect is movement in the bed, right? So big particle usually exposed to the water, to the current, so it tend to be maybe move more than small grain size. So that's this whole hiding exposure effect function. I mean, in the model. So next, I'm talking a little bit about adaptation coefficient. So alpha t early on. Adaptation coefficient. So it's physically it related to adaptation length and adaptation time, right? And adaptation length depends on the grain size. The recommended value is about two times your grain size. So if your grain size is 1 meter, so your adaptation length might be 2-3 meters. But in reality, you need try and error and test this number and see which one fit your purpose. And for adaptation length, first you need to pick adaptation method. So adaptation method. Adaptation method, you can see there's the second panel from the top. You can see adaptation method. You have 4 different options, right? You can pick a constant length. You can pick a constant time. And you can pick a maximum of bed and suspended adaptation length. And you can also pick a weighted average of bed and suspended adaptation length. And corresponding to those methods, sometimes you need to do more. Like if you pick a third and the fourth one, like something related to bed and suspended adaptation length, and you have some other option, like a bed and suspended adaptation length. And you also have way to pick a method. It's a kind of complicated. And you can see for bed and suspended adaptation method, you can also pick constant length, constant time, depth dependent. So this is for bed load. For suspended load, we have 1, 2, 3, 4, 5, 6 method. So for suspended load method, you can pick constant and also constant time and constant coefficient, and also 3 different formula developed by those people. And for our application, most time, to be simplified, we just pick a constant length. And in this case, we pick 10 meter based on our grain size and also some sensitivity test. So we pick 10 meter in the simulation. Yeah. So if you pick some other method, you need to go further down the table and then pick a different method for bed load method and also for suspended load method to get your proper adaptation length through the model calculation. The last one in that interface is avalanche and hard bottom. And I believe hard bottom in Mitch's example, he already mentioned that. So I didn't check here. So here I only check the calculate avalanche. So avalanche is there's a critical bed slope and the angle of repose, and default value is 32. And this one is very important. There's very important for shoreline clap. And we talked to some user lately, and they use they adjust those angle, the angle of repose. They get very satisfied result with the shoreline. I mean, move towards the land, and so if you need this function, you might turn this on and do some test. Yeah, that's about all the presentation slide here. And as I mentioned earlier, the most of the material coming from these two tech report. And there's also, in fact, this model, implicit solver and including net sediment, non-equilibrium total load sediment transport, are first developed by Wei-Ming Wu. He is a professor at Clarkson University, and also by Alex Sanchez. He did his PhD thesis with Wei-Ming. So he introduced this model to CMS. And Dr. Wu has a lot of publication on this model and in different places. And if, I believe most of the reference listed in this tech report. If you check the reference portion of this these two technical report, you will find more reference for you reading and understanding purpose.